Let's talk about 3.1. There's some terminology we need to mention, and then we'll do some examples. The section is on functions and their graphs, and the first term you need to know is a relation. A relation is just a correspondence between two quantities, any correspondence that can be described by a set of ordered pairs. For example, doesn't even have to be numbers. It could be your name, comma, your shoe size, and that would be an ordered pair, and we could do an ordered pair for everybody in here, and that would be a relation. So relation doesn't have a whole lot of specific criteria that it has to meet. Anything that can be described by a set of ordered pairs. The domain of a relation is the set of all x values or input values. We'll talk about why they're input in just a minute. But they're all the x values that can be used in the relation, and the range is the set of y values or output values that can be obtained from the relation. If x is any element in the domain, it's called the independent variable, and if y is any element of the range, it's called the dependent variable, because the value of y depends on the x that you put in. Now, let's get this next definition in the next paragraph, and then go back and revisit those terms and see after an example if you understand better what they're saying. A relation is very general, but a function is very specific. A function is a special type of relation. It's a relation where for each x, there is only one y, or for each element in the domain, there corresponds only one element in the range. For example, you can think of a function as a machine. Your calculator has functions on it. The squaring button is a function. Any function you do on your calculator and hit equals, there better be only one right answer. If you type in a 3 and hit the x squared button, it better say 9 every time. If you hit 3x squared and then equals and got 9 one time, but the next time you entered a 3 and hit x squared and equals, it told you 7, something's wrong. Each x can only be corresponded to one y. You can think of a function as a machine. Next paragraph. You can think of a function as a machine which takes in some number, does something to it, and spits out an answer. That's why I call the x values your input values. You're going to put an x into the machine, and it's going to spit out a y. So the y's are your output variables. If the first time you put a 3 into a machine, you got out a 7, you might go, hey, this is an adding 4 machine. But if the next time you put in a 3, you got out an 8, then the machine's messed up. Every time I put in a 3, I should get out the same answer. Every x value should correspond to only one y value. So the domain is the set of x values that won't tear up the machine. You know, there's some things you can't put, like ball bearings in a washing machine, not good. You can't put anything into the machine that will tear up the machine. The range is the set of y values that can be obtained. X is the independent variable because as long as it's something that won't tear up the machine, you can just pick x to be anything you want. It's independent of anything else. Just pick an x that won't tear up the machine. But y is the dependent variable because the y you get out depends on the x you put in. All right, let's look at these examples. Number 1, if the domain is the set of students in this class, I have all of you write your name down on a piece of paper and put it in a hat. And then, no, don't write it down. Don't put it in a hat. Forget about that. Domain, set of students in this class, and the range is a set of non-negative integers. I'm going to define this relation to be each person's age. So in other words, I'm going to just independently call out someone's name, and that person's going to tell me their age. Does that represent a function? Yeah, because if I call out your name, how many ages are you right now? There's only one right answer to how old are you. So each name corresponds to only one age, So that is a function. And the range is non-negative integers because negative integers don't make sense for ages. But what if the relation was defined differently? It's up to us to define the relation. So what if we said the domain is the set of non-negative integers and the range is the set of all of your names? But this time I'm going to call out an age. Everyone who is that age, raise your hand. Is that a function? If I call out 19, or if I put 19 into the age machine, is there only one person in here who could be 19? No. That's one age that may correspond to more than one person. Defined this way, that relation is not a function. Because for each X, which is an age, there is more than one Y, which is a person. So I'd say no, because for each age, there may be more than one person. Well, if I said how many years have you been in school, then there's only one answer to that. So that would be a function. But if I say how many of you have been in school for 2 years, then that wouldn't be a function because that's a question with more than one right answer. And in math, that messes things up. So all the function keys on your calculator are actually functions. You hit 5 and then the square root button. There's only one right answer to what's the square root of 5. All right. That was a couple of examples that were given to you as word correspondences. The next couple of examples are given to you as ordered pairs. Now, when I give you an ordered pair and ask you for the domain refers to which variable? The x's. So you just list the x's. And usually you write them in braces. I think in homework they'll probably have the braces for you. But the domain of those 3 ordered pairs is 5, 7, and 3. And no. And if my math lab ever counts it wrong because you put 5, 3, and 7 instead of 5, 7, and 3, or you think that's what's happening, click that Ask Instructor button and send it to me. Perhaps I'll see that actually, no, you had 2 commas in there and that's what threw it off or something. But if my math lab is counting something wrong that you think is right, I want to know it because I want to know if it's a mistake or I want to explain to you why your answer actually was wrong. What about the range? Range refers to what? The Y value. So the range of this relation is 2, and there's no reason that you have to write 2, 4, 4. You're just writing what Y can be. Y's are either 2 or 4 in this relation, so you don't have to write the 4 twice. By mapping, I just mean draw a line that shows what Y corresponds to which X. In the first ordered pair, 5 corresponds to 2. So I'm just going to draw a line showing that. In the second ordered pair, 7 corresponds to 4. And in the third ordered pair, 3 corresponds to 4. Is that a function? I have some yeses and some nos. Tell me yes. Tell me why. That's right. Each element in the domain is only corresponding to one element in the range. It doesn't matter that two different x's have the same y. All that the definition of function rules out is one x can't have two different y's. Now, we've been talking about the squaring button on your calculator. If you square a positive 2, what do you get? 4. If you square negative 2, what do you get? 4. So you can have two different x's that give you the same y, as will happen anytime you're squaring positives and negatives, but you can't have one x that's giving you two different y's. You just have to think about that until you get the distinction between the two. Yes, this definitely is a function because each x corresponds to only one y.
So it wouldn't be a function if, say, 3 was a 5.
If 3 was a 5.
There's 2 5s, but there's 2.
Yes. And actually, I think that's what happens in example 4. In example 4, what is the domain? And you don't have to write the 1 twice. If I just say, what are the x's in this relation, you can say, well, they're either 1 or 2. And what's the range of this relation? 2, 3, and 5. By mapping, I just mean draw the correspondence from each x and its corresponding y. In the first ordered pair, 1 corresponds with 2. In the second ordered pair, 1 corresponds with 3. And in the third ordered pair, 2 corresponds to 5. Is that a function? That's definitely not a function because 1x corresponds to 2 different y values. As long as each x is only paired with one y, as long as you don't have one x paired with 2 different y's, then it's a function. If you wanted to add another sentence, just in case it would help clarify something to you on number 3, you could say number 3 is a function because each x corresponds to only one y. Under that, you could say it doesn't matter that 2 different x's correspond to the same y. That's not against the definition. It doesn't matter that 2 different x's correspond to the same y. All right. We've looked at a couple of word correspondences, a couple of ordered pairs. Next few examples, we're given an equation. And example 5, I just used the big fancy set notation to make sure you knew how to read that. This is read, the set of all ordered pairs x and y. This vertical line is read such that. So this is the set of all ordered pairs in the form xy such that y equals x plus 1. Now, all that means is all of the ordered pairs in this relation have a y that's 1 more than the x. So any, miny, miny, mo, give me such an ordered pair. 4 or 5 works. That is an ordered pair of the form xy where the y is 1 more than the x. That's all this set notation means. Give me another one. 2, 3. Somebody go out on a limb and give me Something exciting with negatives in it. Yep. Yep. You add 1 to that x, you get that y. And just for the heck of it, we could say 0, 1. All of those ordered pairs, the y is 1 more than the x. What is the domain of that relation? Well, that's the ordered pairs we made up, but how many ordered pairs actually are there that satisfy that equation? There are infinitely many ordered pairs that satisfy that equation. These are just 4 samples we made up, but the domain means anything you can let x be. So what could you let x be in that equation? Anything. The domain of that relation, you could either write all real numbers, or you could write in interval notation negative infinity to infinity. There is nothing that blows up an adding 1 machine. You give me any number in the whole wide world, I can add 1 to it. What about the range of that relation? What kind of y's can be obtained from adding 1 to other numbers? Anything. You just give me a y that you want to have as the answer. I can come up with the x that would give you that answer. So the range is negative infinity to infinity, just like the domain. Is this relation a function? Yeah. No matter what I punch on the calculator first, if I punch a number and then plus 1 equals, there's only one right answer. So that is a relation because for each x, there is only one y. That is 1 larger than the given x. You give me any x in the whole wide world, there's only one answer to the question, what's 1 more than that? All right, example 6, y equals x squared. How many ordered pairs do you think we could come up with such that the y was the square of the x? Yeah, I mean, I can type any number that'll fit on my calculator and hit the square button and get an answer to it. So there are infinitely many ordered pairs that satisfy that relation. Give me a few. That works. Negative 5, 25. Give me another one. That works. Any ordered pair where the y is the square of the x. Give me another one. Ooh, awesome. I don't want to graph it because I don't want to make 144 tick marks, but it certainly satisfies that equation. And for that matter, so does negative 12, 144. What is the domain of that relation? Not just the x's and the ordered pairs we listed as samples, but any number that you could square. You can square anything, negative infinity to infinity. The range will be the y's that can be obtained from squaring other numbers. What's the range? Oh, if the y's come from squaring x's, then you can't get negative numbers. I didn't say this before, but to be clear, we're talking about real numbers. Actually, you can square an imaginary number and get a negative, but that's not what we're talking about. Within the realm of real numbers, there's nothing that you can square and get a negative. So the range, you said 0 to infinity, is 0 included? Yeah, you can square 0 and get 0. So 0 is the very smallest element in the range, but those y values can get infinitely big. Does that equation represent a function? What about the fact that negative 12 and positive 12 had the same y values? That doesn't matter because 12 only has one right answer to what's its square, and negative 12 only has one right answer to what's its square. So, yes, it is a function because let's say every number only has one square. And the number is the x, and the square is the y. So each x only has one y. One more equation, number 7, is x equals y squared. Give me some ordered pairs where the x is the square of the y. Negative 25, right. Could be 25, negative 5. The only rule is the x has to be the square of the y. That's what this equation is saying. So give me another one. Okay, 25, positive 5. Give me 2 more just for the heck of it. 16, 4, that would work. That x is the square of that y. And then you said 144, 12. That works because that x is the square of that y. Yeah. Any ordered pair where the x is the square of the y. For that matter, 0, 0 would satisfy the equation. So what is the domain? What kind of x's can be obtained from squaring y's? Here you're not going to get any negative x's. If x is the square of y, then you're not going to have any negative x's. The very smallest x you're going to have in this relation is what? 0. But they can get infinitely big. What about the range? Well, the range is the y value, and that could be anything you can square. So what's the... Y can be anything in this example, because you're just going to square it, and you can square anything. Is that relation a function? No is correct. Why? You may have it right in your head. You're not saying it exactly so that it makes sense. There's more than one y for some of the x's. For example, when x is 25, there are 2 different y's, a negative 5 and a positive 5. So that is not a function because one x corresponds to 2 y's. As a matter of fact, it would be true for all positive numbers that every positive x would have 2 y's, because every positive number has 2 square roots, a positive square root and a negative square root. If I just say what's the square root of 100, 10 is the first thing that pops in your head, but negative 10 is a right answer also, because negative 10 squared gives you 100. So I'm going to say no because every positive number, and the positive number is the x, has 2 square roots, and that's the y. So we've looked at word relations, we've looked at ordered pairs, we've looked at equations. The only other way I can think of to represent a relation is by its graph. I can graph a relation and then say, what's the domain, what's the range, and is this a function? This graph, this handout's kind of old, and at the time I did that, that was the best parabola I could do on the computer. I could do better now, but it's kind of shaky. It's supposed to be that nice U-shaped curve that goes forever to the left and forever to the right. So, how do you tell the domain by looking at a graph? What x can be? When you're looking at a graph and you're looking for the domain, just say, how far to the left do the x's go? How far to the right do the x's go? Because that's what the domain is, the x values. So the domain of that function is negative infinity to infinity. And when you're looking at a graph and ask for the domain, just give the x values left to right. If that graph goes forever to the left, forever to the right, then its domain is going to be negative infinity to infinity. What about the range of that relation? What y values are graphed there? The very smallest y value on that graph, the lowest point on that graph, is when y is 0. So 0 is the very lowest y value, and how high do the y's get? Those arrows mean they get infinitely big. So the range is just 0 to infinity. When you're looking at a graph and ask for the range, give the y values low to high. When you write interval notation, you always write it smallest to largest, so you'd write that range 0 to infinity, not infinity to 0. Yes, sir?
I was figuring since you come back down to 0, I didn't understand. Could you write it as infinity, back down to 0, and make your brackets like you used to do with the graphs across the line? How did you
Well, that wouldn't be answering the question, what's the range? The range, when I say what's the range, that simply means what's the smallest y value on that graph, what's the biggest y value on that graph. The graph may be curvy forever, and it might hit 0 several times, but 0 would still be the lowest point on the graph, lowest y value on the graph, and that's the only answer you're giving. What's the lowest y value, the highest y value. Now, how am I supposed to know by looking at a graph whether or not that relation is a function? Ooh, play like you didn't know that yet and you had to figure it out all by yourself. You're absolutely right. But think about the definition of a function. The definition is each x value can only have one y value. For this x value right here, how many corresponding points are there on the graph? Just one right above it. For this x value over here, how many points correspond to it on the graph? Just one. Looks like about right here. What about when x is 0? How many y values are there? Just one. As a matter of fact, for any x on that graph, there's only one corresponding height on the graph. So that is a relation, or is a function, because each x value has only one corresponding y value, and that y value is the height on the graph. Each x only has one corresponding height on the graph. And then what about number 9? What's its domain? How far to the left, how far to the right does that graph go? The very lowest x is 0. And then it does appear to be going forever to the right. So the domain is 0 to infinity. How about the range? Give me the y values on that graph from lowest to highest. It's going forever down, kind of slowly, forever up, kind of slowly, but the range is negative infinity to infinity. Is that relation a function? For this x right here, whatever it is, how many corresponding heights are there on the graph? One above and one below. For this x value, there's 1 point above, 1 point below. As a matter of fact, every x value on that graph has 2 y's, except for one, which one x only has 1 y. Yeah, 0's the only x that only has 1 y. So is that a function? No. Because to make this precise and to eliminate 0, I could just say each positive x value corresponds to 2 y values. And again, the y values are the height on the graph. As a matter of fact, we're going to talk about this some more later, but number 8 is the graph of number 6. You may remember that from intermediate algebra or math essentials. The graph of y equals x squared is this nice U-shaped parabola. And you didn't talk about it in Math 1000, but we're going to talk about it in a couple of chapters. Graph number 9 is the graph of x equals y squared. When you take an equation and just interchange the x and the y, here it was the x that's squared, here it's the y that's squared, it turns the graph on its side. That's always true, but we'll talk about it more later. All right, now when I said how do you tell by looking at the graph whether or not it's the graph of a function, somebody said the vertical line test. That's awesome. Awesome that you knew those words. But even without knowing those words, we figured, basically, we reinvented the vertical line test because we found out that if this vertical line through that first x that I chose touches the graph in more than one place, it's not a function. That's one x that has 2 different y's. So the vertical line test is just putting that into words. If at any place on the graph, a vertical line can be drawn on the graph such that the vertical line intersects the graph in more than one point, then it's not a function, because that's one x with more than one y. So tell me whether or not this is a function. Yeah, there is no place on that graph that I could put a vertical line that would touch the graph in more than one place. As a matter of fact, if you've had any trig or if you take pre-calculus, you'll find out that's the graph of the sine function. If you're not going to take any trig, that's fine. You should still be able to tell me it's a function because any vertical line on there would only touch the graph one time. However, well, that kind of tells you the answer to this question. Is that a function? No, because this vertical line right here touches the graph in 3 places. All right. Very quickly, a few problems from the homework, page 211 in the book. Number 16 gives us a relation where fathers are paired with their daughters. And it looks like in number 16, Bob has 2 daughters, Beth and Diane. John just has 1 daughter, Linda. Chuck has 1 daughter, Marcia. Does that represent a relation? If this is the domain, and this is the range, is it true that each element in the domain corresponds to only one element in the range? That's not true. Bob has lines going to 2 different people. So that is not a function. Because, did I just ask the wrong question? I'm sorry. Yes, it is a relation. I remember now that I said the wrong thing. They are all relations. It's not a function. You answered the right question, and you said the right answer to the question I intended, not the question that I actually said. They're all relations. I mean, a relation really has no restrictions. Anything that you can write as an ordered pair or draw lines between 2 different sets, it's a relation. But specifically, this relation is not a function because one element in the domain goes to 2 different elements in the range, or one father corresponds to 2 daughters. What if this function was defined the other way, though? What if the domain was the daughters and the range was the fathers, and I just asked Beth, who's your dad? How many right answers are there to that question? It may or may not be known, but there's only one right answer. So that would be a function because each daughter only corresponds to one dad. It wouldn't matter that 2 different daughters corresponded to the same dad if that was just defined the other way.
All these charts where the arrows.
Yes.
Whenever I was looking at it, I was like, how do I know?
Yep. And I didn't even notice that, but you're exactly right. All right. Number 16 is a correspondence between level of education and average income. I think I'm way underpaid. The less than 9th grade average income is around $18,000. 9th through 12th grade, but didn't graduate high school. Gosh, I'm not going to say no, but very few folks who didn't graduate high school in Cumberland County are making $23,000. High school graduate, $35,000. Some college, $45,000. College graduate, $67,000. Is that a function? Yes. Each level of education corresponds to only one average income. That's because this is an average income. If this was just income, I could find a bunch of folks who quit school before finishing the 9th grade and say, what's your income? And there would be more than one answer to that. So that would not be a function. But if I take all those answers and just get one average, then that is a function. 19 through 26, if I say, what's the domain? You just list the x's. If I say, what's the range? You list the y's. What I want you to do real quickly is look at those and tell me which of those 8 are not functions. Help me find the ones that aren't functions. 19, because why? 2 corresponds to 6 in the first ordered pair, and 2 corresponds to 10 in the last ordered pair. So that's not a function. What else? 23, because, -2 corresponds to 4 in the first ordered pair, but -2 corresponds to 6 in the second ordered pair. There it is. Yeah, 23 is no, and 24 you said? -4, 4, and -4, 0. Are the rest of them functions? All right. 22, let's see. 22, the second ordered pair and the third ordered pair have the same y values, but there's no ordered pair where the same x has 2 different y's. So actually 22 would be a function. All right. 25. Well, you don't have any 2 ordered pairs where the same x has 2 different y's. -1 and +1 are 2 different numbers, so they could have different y's or the same y, and it wouldn't matter. 27 through 38. How do we look at equations and decide whether or not they're functions? Well, think about your calculator, or think about a machine on number 28 that cubes anything you put into that machine. You have a cube button on your calculator probably. If I type a number and hit that cube button, how many right answers are there? Just one. So is y equals x cubed a function? Yeah. Same thing with 27. If I put in a number, hit the square button, there's only one right answer, so it's a function. What about 29? That's called the reciprocal function. It takes anything you put in and flips it. And actually I have a button for that on the calculator as well. If I put in a 4, what does this machine spit out? 1/4. If I put in a 2/3, what does this machine spit out? 3/2. Is it a function? Yeah, for any number, there's only one right answer to the question, what's the reciprocal of that number? What about number 30? The TI 83 and 84 have an absolute value key. How many right answers are there to the question, what is the absolute value of any number I give you? It's only one right answer to what's the absolute value. So that's a function. What about 32? Y equals the positive or negative square root of 1 minus 2x. If I let x be, say 0, how many y values correspond to x being 0? If I let x be 0, then under the radical I'd just have 1, and then square root of 1 is 1, but I have positive 1 and -1. That's what the plus or minus means. So that is 1x that corresponds to 2 different y's. Is that a function? That is a sideways parabola. Yep. When you say something's not a function, you should be able to make up 2 ordered pairs that have the same x but different y's. Like I said, if x is 0, y could be positive 1, or y could be -1. There's 2 ordered pairs that fit that equation and have the same x but different y's. What about 31? How can I tell whether or not that's a function? If I solve for y, if I got the y completely by itself, in order to do that, what would I have to do? And as soon as you said take the square root of both sides, what bells and whistles went off in your head? Don't forget the plus or minus. So really 31 is just like 32, because if you solved for y, you'd have y equals plus or minus 4 minus x squared. So is that a function? No, for the same reason that 32 is not a function. Do you see one thing in number 31 that could automatically tell you, hey, anything with that's not going to be a function? Anything with plus or minus, or anything with y squared, because anytime you solve for y, you'd have the plus or minus. So if the equation has a y squared, or y equals plus or minus, then it's not a function. And despite what it looks like, a function is 2 words. Not a function. So tell me the others of those that aren't functions. 33 has a y squared. 37, 38. Ooh, what about 36? If I gave you a test question, a 1-question pop quiz, and I said, find y when x is 7, for example, how many right answers would there be? There would only be one answer. If you let x be 7, there would only be one right answer for y. So is that a function or not? Yeah. The only thing we've mentioned that would automatically tell you, hey, that can't be a function, is the y squared, or synonymous with that, y equals plus or minus, because that's where the plus or minus comes from. All right. Page 3. I just asked the question about number 36. I said, if I gave you this problem on the test and ask you to let x be 7 and find y, you could do that, right? If I wanted to give you another problem and let x be 5, I'd have to rewrite the whole problem, let x be 5, and find y. And then if I wanted to give you a third problem where you let x be 0, I'd have to say, let x be 0 and find y. So I'd have to write that. I'd have to write a bunch of stuff for every single problem. Well, function notation is just a shortcut way of writing these functions so that we don't have to say, find y when x is 7, find y when x is 3. Function notation is, well, looks like this. F of x, or that f could be anything. In business calculus, we talk about the revenue function and we call it R of x, or the cost function C of X, or the profit function P of X. But this is just the name of the function, and X is the independent variable. You can let X be anything you want. That's why it's called the independent variable. Anything you want, that doesn't blow up the function. We'll have to talk about that some more in a minute. 3x plus 2 in this function is called the defining expression. It tells you what this function does. This function takes any number that you put in, triples it, and then adds 2. You read that entire expression as f of x, not f with a little x in parentheses by it. That would not be time saving. Just f of x equals 3 times x, or 3x plus 2. There aren't very many times in math that the same notation has two different meanings. Math is usually very precise and unambiguous, but up until you study functions, if you had seen one number beside another number in parentheses, what would those parentheses be telling you? Multiply. So this is one of the only 2 times I can think of that one symbol can mean 2 different things. When you're talking about functions, that doesn't mean f times x. You can't solve for f by dividing both sides by x, because that doesn't mean multiplication. That's just the name of the function. F is the name of the function. X is the name of the independent variable. So now that we have function notation, I don't have to write the whole sentence, evaluate 3x plus 2 when x is 7, and then evaluate 3x plus 2 when x is 4. I can just say, find f of 7. And that means put 7 in place of x and simplify it. Or f of 4 means put 4 in place of x and simplify it. The next examples, we have 3 functions. F of x is a doubling and adding 1 machine. G of x is a squaring machine. And h of x spits out a 7 no matter what you put in. I'm not sure what the role of h of x is in life. A machine that spits out a 7 no matter what you put in. It's actually called a constant function. Number 1 says find f of 2. That means put 2 in the place of x in the function f. 2 times 2 plus 1 is 5. That means when you let x be 2, you get y equals 5. That also means that the ordered pair 2, 5 would be on the graph of that function. Example 2 says find g of 2. That means put 2 into the function g in the place of x. Well, g is a squaring machine, so if you put in a 2, it's going to spit out a 4. The ordered pair 2, 4 would be a point on the graph of the squaring function. Example 3 says find h of 2. If you put a 2 into the h machine, what is it going to spit out? Because that's all the h machine has in it. It's going to spit out a 7 no matter what. The ordered pair 2, 7 would be on the graph of h of x. Notice that when I say 2, 7 would be on the graph of the function, 2 is your x and 7 is your y. This f of x is the same as a y value. It's the y value of the ordered pair. So wherever you see f of x, you could put y in its place if you wanted to. Yes. Yeah, you could write f of x equals 3x plus 2, or you could put y equals 3x plus 2, and those two things mean the same thing. No, because 2 is the x. What is beside the name of the function is your independent variable. That's your x. So x is 2.
X.
No, f of x is the y value. F of x here, or h of x, is 7. That's the y value.
X will be 7 too.
No, this is your x. That's your y. And that's the ordered pair, 2, 7. Uh-huh. No, the left-hand side is not your x. The left-hand side is y. F of x is the same thing as y. You could put y in the place of that. If I just gave you y equals 2, I'm sorry, if I wrote that constant function y equals 7 instead of x equals 7, then one ordered pair that would be on that graph is the point 2, 7. Another point on that graph would be 0, 7. All the points on that graph, the y would be 7. All right. Number 4 shows us an example of adding two function values. We do it in business calculus. It's not calculus when we're doing this, but if we have a revenue function and a cost function, we subtract them to get the profit function. That's how you find profit, revenue minus cost. So here, I don't know what f of x and g of x actually stand for, but I can find f of 3 plus g of -1. Just put 3 in the place of x in the function f, and put -1 in the place of x in the function g. And whatever you get for the value of those two functions, add them together. This would give you 7. This would give you 1. And 7 plus 1 is 8. Unless you go on to calculus, you'll never know why we would ever put variables, other variables into the function. I could say find f of x plus 2, and that would mean put x plus 2 in the place of x. I could say find f of x plus delta x minus 7. Put that in the place of x in the function f. I could say find f of pig, and that would mean put pig in the place of x in the function f. Like I said, unless you're going on to calculus, you won't need to put algebraic expressions into another function. But if you do go to calculus, we'll talk about it some more then. For here, it's just a little practice problem, making sure that you understand f of x plus k means put x plus k in the place of x. So instead of 2x plus 1, we have 2 times x plus k plus 1. Yes, ma'am? Uh-huh. You couldn't write an ordered pair there because, yeah, and you're using two different functions. It wouldn't be the graph of one function. All right. Number 5, if you see a problem like that in the homework, it probably says simplify as much as possible. Just clear out parentheses and combine like terms. On this particular problem, we could clear out the parentheses, but we don't have any like terms to combine. If it says, that's a K, if it says simplify, then if there are parentheses, clear them out. If there are like terms, combine them. Number 40. Find the following for f of x equals -2x squared plus x plus 1. F of 0, just put 0 in place of x. F of 0 is always easy to find because any term with an x in it's just going to be wiped out. You let x be 0, negative 2 times 0 squared is 0, plus 0 is still 0, so all that's left is negative 1. What does f of negative x mean? Do what, Kelly? Whatever's inside that parentheses, that's what you put in place of x. Again, if I said find f of pig, you'd put pig in place of x. So if I say f of negative x, you put negative x in place of x and just see what happens. In place of that x right here, I'm going to put negative x. I need to have it in parentheses to see that negative is part of the base. In place of the other x, I'm going to put negative x. And then just bring down the minus 1. Not a whole lot of cleaning up there. What do you get if you multiply negative x times negative x? Positive x squared. Positive x squared. So this first term could just be written as negative 2x squared without the parentheses. Again, because a negative x times a negative x is a positive x squared. That middle term in algebra, we never write plus a negative, we just write minus. So it doesn't clean up a whole lot, but it's negative 2x squared minus x minus 1. Do you think that E will give us the same answer? Does it mean the same thing? What do you think? How are we going to find negative f of x? I'm convinced that these probably won't give me the right answer.
When you do the opposite, like negative 2x versus positive 2x.
But make sure you take the opposite of the whole thing.
Right.
Yeah. Negative f of x means negative 1 times f of x. That means whatever f of x is, you need to multiply it by negative 1. Clear out the parentheses and you would have positive 2x squared minus x plus 1, which is not the same thing we got for part D. All right. G part, find f of 2x. Use parentheses to show that 2 is part of the base. You have negative 2 times, in place of this x, we now have 2x. It's still squared. In place of this x, we now have 2x, and we still have our minus 1. Very simply, to finish this, 2x times 2x is what? 4x squared, and 4x squared times negative 2 would be negative 8x squared plus 2x minus 1. Ms. Klein? Exactly. And I thought that's what I said. 2x times 2x is 4x squared. Yeah, I did. I said 2x times 2x. That's the same thing as saying 2x in parentheses. Yeah, you're exactly right. The order of operations says square that and then multiply by negative 2. All right. Roman numeral number 3. We have found the domain of a function. If you just give me a set of ordered pairs, I'm going to write down the x's. But what if you give me an equation? Well, we saw some of those. we just said, what can you let x be? For example, number 48, if I was building a machine that took any number that you put in and squared it and added 2, what kind of numbers would it be okay to put in? I can square any real number in the whole wide world and then add 2. So the domain of that function is negative infinity to infinity because you can square and add 2 to anything. But there are some functions, some machines that are persnickety. I wonder if anybody under 20 knows that word. Have you ever heard the word persnickety? But that's the first time? Oh, it's one of my granny's words. Some functions, you do have to be careful about what you put in because you can blow up the machine. Now think algebra here instead of engineering. What blows up an algebra problem? What can you not allow to happen in math? Square root of a negative number would give you an imaginary number, and we're only talking about real numbers here, so that would be a problem. What else would blow up a math machine? 0 where? 0 in the denominator. That's the 2 things you have to watch out for when you're looking at an equation and writing its domain. Any values which give you 0 in the denominator of a rational function or a negative number under a radical, you better put a big old sign on your machine saying, don't put these numbers into the machine. They'll probably still get blown up because people don't read signs. But that's what domain means. What can you let x be? Well, number 54 is a fraction. And the only thing that'll blow that fraction up is 0 in the denominator. What about 0 in the numerator? Isn't that a problem if I had, let's say, 0 over 10? That's just it. No, it doesn't. That's just 0. No, that's not a problem. What makes the numerator 0 is not a problem. Only what makes the denominator 0 is a problem. So if I say, what can you let x be? Maybe you can squint hard enough to figure it out. But if you can't squint hard enough to figure it out, just set the denominator equal to 0 and solve that equation. That is a 2. That's a quadratic equation, so solve it by factoring. If you factor out an x, it leaves you an x minus 4. So what 2 numbers make that denominator 0? When I say, what's the domain? I'm not asking, what can you not use? I'm asking you, what can you use? So the answer would be anything but 0 and 4. And the easiest way to write that is x cannot be 0 or 4. That's the sign you better hang on the machine, because as soon as somebody comes along and tosses in a 0 or a 4, your machine's broken. All right, number 58. I have 2 things to watch out for. Not only can I not let x be anything that would give me 0 in the denominator, but I can't let x be anything that would give me a negative under the radical, because I can't take the square root of a negative number without going outside the realm of real numbers. What kind of numbers could I subtract 4 from and still get a positive? Anything bigger than 4. Yeah, I was afraid somebody might say anything bigger than 5, but then I was going to say, what about 4.5? 4.5 would be okay. 4 and 4.00001 would be okay. But it does have to be bigger than 4, or else when you subtract 4, you'd get a negative. Just set that radicand, whatever it is, has to be greater than 0, can't be equal to 0, or you'd have 0 in the denominator. And now you're solving an inequality rather than an equation. Just add 4 to both sides. If I didn't specify interval notation, you could just leave that for the domain. The domain is anything bigger than 4. If I do say write your answer in interval notation, then you would write 4 to infinity, but make sure you had a parenthesis on the 4 because you can't let x be 4. It makes that denominator 0. All right. 4 minutes, 2 problems. We can do it. Or at least part of it. This is your favorite problem in the whole wide world. I've been excited all hour waiting to get to this rock falling on Jupiter again. If a rock falls from the height of 20 meters on the planet Jupiter, its height, h, after x seconds is approximated by this formula. First thing you better figure out is what the variables stand for. What is h? H is the height. And what is x? It's a number of seconds. So the A part says, what is the height? That means find what? Which variable? H. Find h in 1.2 seconds. 1.2 is the x. Just find h of 1.2. 20 minus 13 times 1.2 squared. We're not going to take time to punch that on the calculator, but that's what you would do. No, I didn't have that with me. The B part, what is the height of the rock? Oh, when. Okay, when is the height of the rock 15 meters? When means I'm solving for which variable? The x, the time, when the height is 15. So let height be 15 and solve for x. You'd have to subtract 20 from both sides and then divide both sides by negative 13. Negative 5 divided by negative 13 is just 13. 5/13. Take the square root of both sides, but you don't have to worry about the negative square root because this is a time and a negative time doesn't make sense. We're not going to take time to punch that on the calculator either. All right. See, when does the rock strike the ground? When means we're solving for x, but if I'm solving for x, you have to give me a height. What is the height of the rock when it hits the ground? So we're solving the equation 0 equals 20 minus 13x squared. That's a very sad 20 there. And you solve it just like you did the B part. Subtract 20, divide by negative 13, take the square root. All right, 30 seconds. I need to tell you something about 104. We don't have time to finish it, but I've got to just tell you how to start it because there's one like it in the homework. Suppose that the cost of manufacturing X clocks is given by this big old cost function, and the clocks are sold for $30 each. What's the revenue function? If you're selling clocks for $30 each and you sell, say, 10 clocks, what's your revenue? 30 times 10. So if you sell X clocks, your revenue is 30 times X. 30 times however many clocks you sell. The profit function, I mentioned this a while ago, profit, the definition of profit is revenue minus cost. We found the revenue function in the A part, and we were given the cost function. Just simplify that. 30x minus the cost function would be negative 0.1x squared plus 23x minus 400. All I did was distribute the negative completely and combine like terms. Yeah, negative 0.1. No, that's my bad. I'm in a hurry. Negative 0.1x squared plus 23x minus 400. And then to answer the C part, we won't even write this one down, but how do you find P of 30? No, that doesn't mean P times 30. P of 30 means what? Put 30 in the place of X. And this function right here, that would get, it says find and interpret. The interpretation would be, that's the profit if you sell 30 clocks. Alrighty, thanks for giving me an extra 2 minutes. I owe you. I've let you out 2 minutes before. I don't owe you.